Good evening, URI ELECOMP Capstone. We are Project EchoMike 2. We're sponsored by the charity SANCTUARI, and our project pertains to a post-release tracking device for small mammalian species. I'd like to take a second to introduce all the members of the EchoMike design team. Firstly, we have Barry Huang, an electrical engineer, myself, Jack Russo, an electrical engineer, Ismail Mohammed, an electrical engineer, and Amani Hamid, a computer engineer. Before we get into the project details, we'd like to thank this project's dedicated technical directors. Class of 1981 URI Ely graduate with decades of industry experience, Chris Rothwell, and Sanctuary's dedicated founder, Joe Morera. They both have provided a clear direction and invaluable feedback throughout our design process so far. The need for a wildlife tracker is painfully self-evident to a conservationist the moment they release an animal they've spent months caring for into the wild and lose contact almost entirely. This project has a clear goal of improving tracking capabilities for small mammals after they are rehabilitated and released in a way that prioritizes non-obtrusiveness. Our design is set to offer valuable benefits in an undersaturated market in terms of cost, configurability, and ease of use.
SANCTUARI is a non-profit wildlife care organization dedicated to improving survival rates by utilizing modern technology, document and share proven methods in wildlife care grounded in the latest scientific research. SANCTUARI economic impact can be summarized by provide essential financial, technical, and logistical support to reduce the burdens on wildlife resources. By collaborating with like-minded organizations, SANCTUARI amplify the impact on wildlife care and conservation, and also by promote animal rights, habitat protection, and adoption of green technologies, and its commitment to high standards ensures resources are used effectively for maximum impact.
This project aims to successfully design, prototype, and test a small, lightweight, wearable, long service life tracking device suitable for smaller mammalian species such as fox, raccoon, skunk, possums, rabbit, and more. More specifically, this project aims to be 5% of the animal's weight, ensuring it will not hinder the animal's survivability in the wild. The tracking device aims to be operational in all types of environment. Lastly, a user-friendly app will be implemented to customize the tracking device functions so that what kinds of data and how often it is collected can be tailored to each animal needs and environmental requirements.
This was our key technical accomplishments for this semester. Our team selected the ultra-low power BG24 microcontroller with Bluetooth and the BG77 cellular module with GPS and cellular. We established a UHART interface between them, enabling GNSS data retrieval on the BG77. We chose a cellular provider, ordered a SIM card for NB-IoT communication, and integrated the BG24 and BG77 into the PCB design. We developed a software interface in Simplicity Studio, created a GNSS configuration template for the BG77, and outlined steps to send data to the cloud. Additionally, we began developing the Flutter app and firmware for the BG24.
This is a simplified diagram of how each component flow and interact with each other. The tracking unit receives tracking data through the GPS and collects other sensor data, and then the module pushes the data into a cloud database. A custom phone app is capable of pulling the data from the cloud and neatly displaying it to the user as well as configuring the tracking unit. For my technical contributions, I researched the datasheets, schematics, and user manuals for the BG24 and BG77 modules to understand their design requirements. I also reviewed datasheets, blueprints, and schematics for other components needed in the design. I created schematic symbols for the BG24 and BG77 and developed the complete PCB schematic, ensuring proper integration to all components. I sourced parts from DigiKey, Quectel, Infineon, and Silicon Labs, considering availability and compatibility. Finally, I laid out most of the components for the PCB. These are the list of parts I personally contributed to the schematic. By referencing similar development kits and applications examples provided by the components manufacturer, I was able to create a system schematic that utilizes all these parts tailored to our design. Here we have a block diagram that outlines the key components of our PCB design and show how they are interconnected to achieve the system's overall functionality. On the left, the BG77 handles the GPS data. The BG24 microcontroller serves as the brain of the system. It processes data, manages signals, and coordinates the overall operation of all connected components. The power isolation block ensures efficient power usage by disconnecting unused circuitry. Moving on to the PCB, these components are placed in a similar way of the dev kits, guaranteeing the functionality of the component. Since this is the first prototype, there are many requirements to address, such as the sizing of the board. As we move forward from debugging and testing phase, we will end up removing certain components, making the PCB smaller. My remaining task involves ordering the PCB and testing the PCB. Once we are satisfied with the prototype, I will begin finalizing the PCB for a production-ready version. Finally, I will design the housing for the tracking device. And now I'd like to introduce our second designer, Jack Russo.
Hello everyone, I'm happy to give insight into my technical contributions on the project. I have mainly contributed to the development of using Silicon Labs microcontroller, the BG24, in our project. In relation to the hardware, I have accomplished tasks such as integrating sensors and RF circuitry. On the other hand, I have contributed to the development of the firmware application running on the BG24 by initializing all the necessary components, organizing the Bluetooth stack, and testing methods for communication between two devices. Specifically in designing the firmware, establishing a working UART connection to the BG77 was the first priority. In testing, I was able to initialize and send out data on the BG24's transmit line as pictured on the oscilloscope. This has been developed further to easily send commands to the GPS module that instruct it to calculate location of the device. The firmware capability of Bluetooth configuration and commands was next to be implemented. The initial setup and understanding of the Bluetooth stack was an important step in enabling future use of the Flutter application in the device. Lastly, I've made efforts in enabling and collecting data from all the peripheral devices included in the system. Additionally, I was able to lend myself to designing the schematic for our custom PCB. Some example circuitry that was designed by me pictured above includes the accelerometer, the switches for turning on and off power to peripheral design components, and the RF and wireless components like the antenna and the crystal oscillator. The Bluetooth utilization of this design is made to be simple and lightweight. The server hosts one service that is important to the functionality of the system. Within this service, there will be a characteristic that contains a single .json document. This document will control the configuration options, system health information, and commands for things like starting and stopping tracking. We will be parsing this document on a microcontroller with imported open source JSON reading and writing libraries. The tasks remaining to reach our ABO that I feel I will be able to technically contribute to and take responsibility for include aiding in designing and debugging the PCB we order, incorporating more options for saving power, sending the data collected to the cloud database, and much more. Thank you for your time. I'd now like to introduce designer number 3, the computer engineer for our team, Amani Hamid.
Hello, I'm Amani. My technical contributions to the project include designing and implementing a cross-platform application using Flutter. The app is built to provide an intuitive and seamless user interface, enhancing the overall user experience. I integrated AppRide as the backend to manage real-time data and user authentication, ensuring secure and efficient data access and synchronization between the app and the cloud. Additionally, I started implementing Bluetooth Low Energy functionality using Flutter Blue Plus, enabling real-time communication between the app and the tracker device for configuration and monitoring. For the home screen development, I designed and implemented the logging screen, which serves as the app's home screen. This screen was carefully crafted to ensure a clean and intuitive user interface, providing a seamless onboarding experience for users. As the picture on the right shows how you can sign up, shows the entry screen by entering your email and password or log in and sign up. For the Bluetooth integration, I started implement the Bluetooth Low Energy using the Flutter Blue Plus package. This work successfully established connection with the BLE devices, demonstrating the app's real-time communication capabilities. This is a key step toward enabling seamless interaction between the app and tracker device for configuration and monitoring. For the remaining tasks, I will write and implement the code to pull up real-time data from the app's backend to ensure the app stays synchronized with the latest information. Once the data is retrieved, I will ensure its display on the app in a structured and user-friendly format, providing users with a clear real-time insights. I will extend the BLE functionality to include full configuration and monitoring for the tracker device. This will allow users to interact with the device directly through the app. Finally, I will optimize BLE code for reliable device pairing and efficient data transfer, ensuring the connection remains stable and fast. These tasks will complete the integration and make the app fully functional for real-time communication and data management. I'd like now to introduce designer for electrical engineer Ismail Muhammad.
Hello, my name is Ismail Muhammad and I am an electrical engineering senior. For our project, I focused on configuring key hardware and software components. My main contributions include setting up the BG24 for Bluetooth, configuring cellular service, and enabling GNSS for precise location tracking. These tasks were crucial for the functionality and reliability of our mammalian tracking device, small mammalian tracking device. So for the BG70 setup and configuration, I added necessary components like the antennas, and created an outline to integrate its usage into Simplicity's studio code. For setting up cellular service, I researched Internet of Things cellular provider, ordered a SIM card, and set up a tracking system for performance monitoring. I also created a step-by-step guide for configuring a cellular service and attached a cellular antenna to the dev kit. For GNSS configuration, I developed a guide with AT commands to configure the BG77 for GNSS data and tested the setup using a terminal. For our future technical that we wish to accomplish, we want to finish the PCB, develop firmware for the BG24 and BG77, complete the Flutter app, minimize power consumption, and ensure reliable GPS and cellular communication. For our confidence in risk tracking, our biggest risk is failing to establish communication between dev kits. The second one is developing a PCB too late. And the third is app-write backend being insufficiently developed. We're confident we can overcome these issues with the guidance of our technical directors and collaborator efforts. We believe that we will mitigate the risk associated with our project.
At the end, I would like to thank the people who made this happen, our program director, Dr. Harris Sunak, and our technical directors, Joe Marira and Chris Rothwell. Also, a special thank to Mike Smith for the PCB development assistant, and thank you all for listening.